I go on full screen, so I can, yeah, the topic that we had chosen for today, because it's something I've been spending quite a bit of time, is RDF, linked data, ontologies, and how Neo4j integrates with all these technologies. I was asking Maxim before if he was familiar with RDF. Let me replay the question. Is it something you guys have come across? I mean, are you familiar with the whole semantic technologies stack, like RDF, OWL, etc., or are you completely new to it? It's just for me to understand where I'm starting from and not to say things that might be irrelevant for you.
Koji? Mike?
I'm very unfamiliar would be my answer.
Okay, perfect, no problem at all. That's
Koji?
great. Because
what about Koji?
Hi.
Are you familiar with RDF, Koji?
Not so much.
Okay, perfect, no problem at all. So I can, that's great, because I was planning I was planning this as an introductory session, so it's absolutely fine. So let me start spending a few minutes explaining what RDF is. So I'm going to go on full screen mode, and well, that's me. I guess you can reach me on Twitter, but also through my email or many other channels in the Neo4j community as well. But yeah, I mean, RDF is what you see there is kind of the definition from the W3C. So it's a W3C standard. The W3C is the W3 consortium, is the standard. I mean, the body that defines standards like like HTML, like XML, like CSS, etc., and some others. So RDF is a model for data exchange in the web. So what's interesting about it, and the reason why we're talking about it today, is because it represents the data as a graph, and that aligns very well with Neo4j. So you can establish the analogy with something like XML. So XML represents the data in a hierarchical way. Well, RDF, we're going to see in a little bit of detail today. It's a way of exchanging data pretty much in the same way you do with XML or the form JSON or many others, but it happens to represent data in as a graph, as connected entities. So at the basis of it, there's the notion of a triple, right? A triple, and we're going to see some of them in a minute, but a triple is a statement, right? Is what they describe it as a subject, predicate, object statement. For example, Jesus works for Neo4j. So you have an entity which is Jesus, works for would be a relationship, and Neo4j would be another entity, right? Jesus is friends with Karim, so Karim is another entity, and we have a friend relationship between each other, right? So you see that this way of representing the world in terms of triples, statements, ultimately forms a graph, because every triple is an edge in a graph. So if you combine all these triples, that forms a graph, like I was saying. So it's a standard, so it's been around for a few years, and you may or may not have come across it. It can be serialized in many formats. So the notion of triple can be expressed in XML. It can be expressed in JSON. There's many. I'll come back to them in a minute. But it's a standard that also has a query language. So you can query a set of triples using a standard query language, which is called Sparkle, and it's based on triple patterns as well. It would be the equivalent of Cypher. I understand you're all familiar with Cypher, of course, but it's based on triple graphs, so triple models, right? There's an additional element, which is the notion of a URI. A URI, as you know, is a unique identifier in the web, and that's the way RDF represents or identifies things. So now, if we try to establish the analogy with the property graph that we know and that we are used to, which is the property graph Neo4j, we're going to see that there's a direct match. And I was thinking, let me use probably the first graph that you see when you download Neo4j, which is the movie database, right? So this is just a little fragment with the matrix. And you remember that in these graphs, there were nodes representing movies and nodes representing people, right? And people could be either actors or directors or producers. So if you think of this fragment, we're seeing there a node representing the matrix and another one representing Lily Wachowski, and there's a direct relationship. I mean, she's the director of the movie, right? And then movies also have attributes, and you see them here at the bottom, right? Things like the release date, the tagline, the title, etc., etc. So what would that graph that we're used to look like in serialized as RDF in terms of triples? And I'm going to superpose it here, and that's actually RDF, what you're seeing there. So first thing you notice is that things are represented with URIs, as I was saying. So for example, here I'm using a naming that I've made up, but individual one would be the node representing the matrix, the movie, right? So for this individual, we have a number of statements, a number of triples. And the first one I'm saying is that this node has a property called title, which is the matrix. It also has a release date, which is 1999, has a tagline, has a type, which is the movie, and it is connected to other resources. Resource is the terminology in RDF to identify things, nodes in the property graph world. And we see that individual 7, which is, as you can see down here, Lily Wachowski, is connected to individual 1, which was our node representing the matrix, through a directed relationship, right? We see that there are other nodes, other resources that are also connected to the matrix. In this case, individual 6, I don't know who that is, probably one of the actors or anyway. But you see that there is a way of expressing exactly the same information that we had in the property graph, but in the form of triples. And this representation that you see, which is essentially a sequence of triple after triple in a text-based format, is what's called an N triples format. So it's one of the possible serializations of RDF. And back to the serializations, and I'm probably not going to spend too much time on that. You see that there's many more. So because RDF, and it's important, just a little bit of context, RDF was conceived as a way of exchanging data in the web. So it was all about interoperability. So if you've been around for long enough, like I have, you probably remember in the early 2000s, probably, yeah, actually 99, 2001, this notion of the semantic web that people like Berners-Lee or Jim Handler were, talking about, and this was an idea that they came up with, which was essentially let's express the information in the web in a structured way, in a well-defined manner, so that it's easier for let's say agents, for software to make use of it, instead of having it only in web pages, which are basically for human consumption. So that's where it all came from. And so RDF was the kind of the building block for this vision of the semantic web. I'm not saying that semantic web had a lot of adoption, but there are things in that space. But RDF persisted as a way of exchanging graph data. So all this to say that it's all about interoperability, and therefore you have multiple serialization formats depending on what your parser preference is, or what the purpose of your data exchange. And you see the one that we're seeing is here at the bottom, the N triples one, where you see just a sequence of triples, but you can basically express the same in a JSON format, JSON LD, which is pretty popular these days as well, as a way of encoding metadata in web pages. There's RDF XML, which is an XML-based serialization, pretty similar. And there's another one which is more kind of human readable, which is Turtle. That's the name. Let me take a pause here and see if we're following. Does that make sense? Any questions so far? Very good. I'll take that as a yes.
You guys can also use the chat room too if you prefer to do that.
Yeah, no, that's pretty clear.
Okay, perfect, right. So just very briefly, I mentioned that RDF has a standard query language, which is called Sparkle. And you see at the left, on the left side of the screen, an example query, and to the right, the equivalent in Cypher. So the question essentially is, in an imaginary model, in a kind of think of a social network model, who likes a person named Stefan? So liking as in I hit like on a tweet, or I hit like on a picture that you post or whatever. So so in Cypher, I guess you're all familiar with it. So it's easy to see that we're looking for a simple pattern where we have a node. We can specify the type or not, but basically we're trying to find a likes relationship, right? So something that likes something else, that is a person, and we want to filter by name, and saying that we want to find who likes that person called Stefan. Well, the same thing in Sparkle would look as you see here in the left. It's basically decomposed again in triples. So the way you would say that someone is a person and that someone likes someone's name is Stefan is in a number of statements, in a number of triples. So we have here a, which is a variable. It's an alias, which would be the equivalent of the alias that we're using in Cypher. So we say that the type of this node is a person, right? Same as we're doing here. That the name contains the word Stefan. That's using regular expression notation, as you can see. So, but essentially, it's pretty much the same. And then once we identify this node that has a name of Stefan, then who likes that node? So the first thing, as you can see, is that RDF is essentially pretty much an atomic decomposition of every single bit of information in a graph. So in a graph, we have it a bit more. It's a bit more compact in the sense. If I go back to that slide, let me come back to the triple decomposition of these. I mean, if you see the matrix is an entity in the graph that has internal structure. It has properties. It has attributes. In RDF, it's kind of broken down in a list of statements and a list of triples, and that's basically the essential difference between property graphs and RDF. So there is a query language because there are specialized stores. There's data stores that are specialized in storing RDF data, and these were called originally, still are called triple stores. Not very original, but triple stores. Recently, some of them are like to call themselves more like semantic stores or semantic graph databases. But in this space, you probably have heard about companies like Stardog, or there is GraphDB, I think it's called Ontotext. There is SmartLogic, Neptune, also have both a property graph and an RDF graph. So there's a number of vendors that offer support and specific storage for these type of graphs. And if we look at, we've looked at the difference between the property graph, how Neo4j stores data and how RDF stores data, but we can look at it also from the point of view of the data store. And if you think of it, what would a data store that stores triples look like? A triple is 3 elements, so it will look pretty much like a table with 3 columns, right? It will probably have 1 or 2 additional ones for context, etc., etc. But that's exactly what they are. So they are. It's a big column store, which is strongly index-based, of course. So it's in that sense, it has some of the limitations, or well, I wouldn't call it limitations, but some of the problems that relational databases have. So if I understand you're familiar, you probably have attended some of the previous Ninja sessions, and I think Max DeMarcy, also emphasizes in this aspect how our data storage is essentially different from index-based ones. So we, as you know, in Neo4j, we persist the connections between data points. We keep a pointer between a node that's connected to another node, and that way we make it lightning fast to be able to navigate from one node to another. Whereas in index-based stores, you have to scan an index to find what you've seen what a triple looks like. If you say that Jesus is friend of Karin, then you have to find do another scan to find Karin, and all we know about her, what her name, where she lives, etc., etc. So it's a lot of when you navigate the graph, there's a lot of index scanning behind the scenes, and that's absolutely fine. It's just different to what we do. But the reason for that is that, and if you think where it comes from, RDF was typically used for mostly, additive or slow changing data stores, and some common ones that we're going to be looking at are the Wikidata or the DBpedia. So these big community maintained data stores where it's more about adding information than exploring it in a transactional way, in a fast way, in real time. So it's typically used for more analytic workloads. So that's these are some sort of common characteristics of RDF stores, whereas as you know, Neo4j is focused more on not more, but not only, we can cover the analytics side of things, of course, but we also have the possibility of being a transactional store, where both read and write and deletion also is important. So integrity is key, and performance is also significantly improved compared to the strongly index-based stores. Good. So now, I'll stop here with an introduction. So what we're going to do now is look at how does that link with Neo4j, and how you can essentially import, export RDF data out of your graph database, Neo4j. And so I'll say that's enough as an intro, and we just take some examples of RDF and use them with Neo. So what we're going to be using is this extension that's part of our Neo4j labs. So you might be familiar with the labs kind of incubator. So there's a number of projects in our labs initiative, which are developed mostly by the DevRel team, but also by some other members like me, but basically from someone within Neo4j. But it's fully open source, and it's still not part of the main product of Neo4j, but it's kind of in this middle ground, and eventually will make it as part of Neo4j or disappear if there's no adoption from the community. And in this space, we're probably familiar with things like the Kafka connector, or with the APOC library of procedures, or the ETL tool. So there's a number of extensions to Neo4j that help you going beyond what the product does out of the box. And Neo-semantics in particular will help you integrating with RDF data in a number of ways that we're going to see. So this is the URL there at the top that you can go to, and it will take you to a page that looks pretty much like the one in the center. And I mentioned this because from there you will have access to everything. So you will have access to the source of this module. You will have access to the documentation. You will also have access to a number of videos, tutorials, examples, blog posts of how to use it. And you will also have access to the Graph app that we have created. Adam Cowley has created, which is another member of the DevRel team. That makes it very, very easy to use these extensions. So that's your kind of home page for Neo-semantics. Good. So what does it do? Well, Neo-semantics will help you doing a number of things. So the first one is be able to import and store RDF data in Neo4j. So we said that RDF was typically stored in triple stores. That is one possibility, but the reality is that RDF does not impose any way of storing the data. So RDF is a data exchange model, and how you persist your data is your business. And Neo4j is one possibility. So we can consume RDF and persist it in a lossless manner. By lossless, what I mean is that we can then regenerate exactly the same RDF that we had imported after being persisted in Neo4j. You can also export on demand your property graph. Let's say any graph that you have in Neo4j can be presented as RDF. So you can exchange, you can publish, you can expose your graph as RDF for RDF consuming applications. You're going to see how to do that. And we can do some other interesting things like mapping models. So you may have a graph in Neo4j and you want to make it public as RDF, but you want to publish it according to a specific vocabulary. So you want to use a particular terminology. And there are some specific public vocabularies out there that are pretty common, things like schema.org. I don't know if you've heard about it. Schema.org is defines a set of common terms in different domains. So you may want to publish your data according to that standard. If you're in the finance industry, there's things like the FIBO ontology. You might have heard about the notion of an ontology. An ontology is in a way a vocabulary, is a set of terms and how they relate to each other. So you can use that as a way of publishing your data in a standard manner. So you can define this mapping on the fly. So you can say, okay, I want these nodes, my nodes in my graph, I want them to be presented as node type X, type Y, according to these public vocabulary. So that's something that you can do also with semantics. And you can do something quite interesting, which is model validation. So one thing that you can do, well, you know that in Neo4j you can define constraints, right? So you can say, for example, there is this property that is required for nodes of this type. Let's say every person node needs to have a name, for example. And then when you define this kind of constraint, well, Neo4j will not let you instantiate a node of type person without creating that property name. It will consider it a violation. But there are more sophisticated constraints, things around, for example, the types at both ends of a relationship, or the cardinality of a relationship, how many things I can connect from a node of this type, or what's the data type of this property, or what's the specific format of a string in a particular property. So all these things can be expressed in another W3C standard called Shackle, which happens to be serialized as RDF. So that's something that we can also use and leverage in Neo4j through neo-semantics. So I'm going to give you an overview of some of these features with some simple examples. Does that make sense? Is that something that, I mean, are we following okay? Does that sound useful? Again, I'll say that is a yes. If not,
you guys can respond.
Yeah, if you're not happy, you have to complain. If you don't, then I assume you're happy with what I'm saying.
I definitely agree with that.
Good. Okay. Right. So first thing, we're talking about importing RDF into Neo4j. So there's plenty of public RDF datasets out there. So I've mentioned DBpedia, Wikipedia, so Wikipedia, Wikidata, which is the kind of structured RDF structured version of the Wikipedia plus many other data sources. But there's lots more. I mean, I've worked with, again, depending on which sector you're in, but if you're in the finance space, you might have used the Thomson Reuters dataset with the Perm ID dataset, where you have information about organizations, stakeholders, who are the managers of certain organizations, et cetera, et cetera. So there's plenty of datasets published as RDF. So I'm going to use a very, very simple example for this session, but nothing stops you. And in the examples, the videos and the blog posts that I mentioned before, you will find more advanced examples with larger volumes and with bigger data sets, and in particular the ones that I've mentioned. So let's say we have a public RDF dataset and we want to import it in Neo4j. So pretty much what we see in this diagram. So we have a document expressed in RDF, and I'm going to import it in Neo4j. So what I'm going to do is let me stop my my deck here, and I'm going to bring up our desktop, Neo4j's desktop. So what I've done is I've created I've installed 405. I mean, you can work on any full version of Neo4j. So that was, and I've already installed Neo-Semantics. So I'm sure you've been through that process before. So if you go to manage, you can either install some plugins from here. So you can install APOC or some other plugins, or you can go to open the plugins directory, and that should probably bring. Oops, yeah, it's open it in a different window. Let me bring that to where we were, to desktop 2. Here we are. So, and I've already copied there APOC and Neo-Semantics. So Neo-Semantics, you can download it again from the page that I mentioned before. It will take you to the GitHub repository, and all you need to do is download the jar with the latest release. So I've just copied that, restart the database, and you're ready to go. So what I have, and you should have if you give it a try, is something like this. So you have an empty Neo4j database by default, or with your Neo4j default database. So I was saying that I'm going to try to import some RDF data. And one thing that I'm going to do as well is bring up the documentation. So that's the link to the documentation that I mentioned before. And if you go to section on importing, we can take what's the simple example. So there's a number of ways in which you can do that. So here is a fragment of RDF. Now that you are RDF experts, based on after my introduction, you probably see what's going on here. So I'm describing something that's called Neo-Semantics. It's an acronym that you used to do, which I'm saying that is of type Neo4j plugin. It has a number of properties called version, release date, and runs on. And runs on is a relationship that connects it to something else, which is Neo4j 355. This Neo4j 355 is this unique identifier that I was talking about before. So if you see, it matches these one down here. So basically, I'm establishing a connection between this thing called Neo-Semantics, which is a plugin, and we're saying that it runs on these other resource, which is called Neo4j, and it has 2 labels. It has 2 types: graph platform and awesome platform, because we all know that it's an awesome one. And it has a version as well. And like that, we have some others. We have APOC also, some of the older versions, and we have the GraphQL, Neo4j GraphQL plugin. So there's that fragment of RDF describes 3 plugins, and they're all 3 connected to Neo4j 355, right? So that's what we have here. So what I'm going to do is I'm going to create a database for import. So for example, let's do import RDF. We're going to use this database. Go here. There you go. So we're in this database. It's empty at the moment, but what I'm going to do is I'm going to try to import RDF. I can do that directly from here using store, because in the end, I mean, the extension is implemented as a set of store procedures. So I could call them from here and say call Neo-Semantics, and NS is the acronym. And oops, that's not. Let me reload, because sometimes it doesn't pick up when it's a new database. Let's go again to RDF, because I want the auto-completion. There you go. So we have NTNS, and we can do RDF, import, and there's a number of methods there, fetch, inline. But rather than going through them like this, what I'm going to do is I'm going to use the graph app that I was mentioning before, because that was created by Adam Cowley, and it's a great one that we're going to use to. You can start it if you're in a Mac from here, or if not, you can go to the to your installed apps in the desktop, and you can just run it from here. You can say, let's run Neo-Semantics. So the first thing is missing the plugin. I think, no, it's already there. Maybe it's wondering why it's not there, but it is there. Let's connect to the active graph. Well, the first thing is I have set which database I wanted to connect to, and I'm going to use the import RDF. And like you can see there, it's going to, I mean, it's telling me that this constraint is required. So I'm going to accept it. All I'm doing is creating a unique constraint and saying that every resource that we import will have a URI property, and that will be unique. So that's the unique identifier that we were talking about before. So I'm going to create this constraint that does not obviously add any data to the graph. It just creates the constraint. So what are we going to do? So we want to import some data, right? So before I go there, we have to do an initial setup. We have to configure the graph. We have to tell the graph how we want to deal with RDF. And there's a number of options that we can look at. But for now, I'll keep all the defaults. So you can see there's a number of properties that you can configure here. But I'm going to just leave the defaults. And you can see that every action that I do through the app is showing me the cipher code that I need to run if I wanted to reproduce it programmatically. So I'm going to create this configuration, and this is just created an object in the graph saying how am I going to deal with the different options when importing RDF. Let's ignore that for now. I'll come back to it in a minute. So we're about to import some data, right? And we had this example here. So we can either copy paste it, or we can access it also. You can see it's published in this URL. So we could either access it by URL, or we can copy paste it. Let's copy the URL as a first attempt. So before going to the input, I'm going to go to preview, because that's an interesting thing that we probably will want to do before actually importing. I want to be able to see what my data is going to look like before I actually persist it in Neo4j. So you can import RDF in a number of ways. I mean, you can retrieve it from a URL, which is what we're going to try first. But you could also do copy paste. I mean, if you have a fragment like we were saying, you can just literally copy it there and have it parsed and imported. You can upload it from a file, or you can run a Sparkle query. We mentioned before. Well, Sparkle has a type of queries that can return RDF as result. So I could run an Sparkle query on a data store and consume the results of that query directly in Neo4j. If we have time, we might be able to try the others, but for now, let's say I'm going to retrieve it from a URL, and all I'm going to do is copy this URL here. And I need to specify what's the input format, because like we mentioned before, there's a number of different serializations. This one in particular is turtle, so that's what we saw before. It's the more sort of human readable, so that's the one I'm using. And so I select the type, and I'm going to preview the data. So if I select the table view, all I'm going to see here is every single triple that has been parsed. So this is all the information when New Semantics has tried to read that file from this URL. That's okay. That's not very, I mean, probably not the nicest thing we can do, because we want to see it as a graph. So if I do that and I do a preview, now I see it as a in a nicer way, as a graph representation. Let me make that a bit bigger. And we see a number of things. Well, as expected, we have 3 entities representing 3 plugins. So one of them was New Semantics. The other one was Neo4j GraphQL with the properties that we saw, right? The release date, the version, etc. And the other one was APOC. And we see that they're all connected through runs on with a central node, which is the awesome platform, the graph platform Neo4j. Well, the first thing that you see is that everything is prefixed with this NS0. And why is that? Well, we mentioned before that in RDF, everything is uniquely identified with URIs. Right? So that means that not only things, but also the names of things. For example, when I give a name to a property, or when I give a type a name, I have to uniquely identify it with a URI. And you can see that here. We're saying that Neo4j down here is a graph platform, but this graph platform is prefixed with Neo4j VOC, which has a definition up here, which is this one. So if you're familiar with the notion of namespaces in XML, that's essentially it. So we're defining a prefix for a namespace, but the real name of this graph platform is all these URI, right? These followed by graph platform, right? So I mentioned before that we want to be able to regenerate the RDF once we've persisted in Neo4j. So if we want to make that happen, we can do several things. So we can either name things like that, and it might look a bit horrible. So let me show that to you quickly. So if I could go back to my config and I say, hang on, I want to keep the URLs. That's one option. So keep URIs and change. So if I change my config and I use this one and I come back to preview, when I do my preview, look at the names of things. So that's keeping all the names with the long identifiers. If you think what would look like to query that with Cypher, it would be pretty horrible. Can you imagine the kind of query that you'll be writing if you have to specify that the type is named like that? Not very nice. I mean, it's an option. I'm not saying no one will ever use it, but it's not the ideal one. So one thing that we can do, again, if we want to be able to regenerate that, is to use this sort of prefix notation. So I'm going to replace the namespace part by defining these prefixes. So this is what the default option does, the shorten option does. So I'm going to change that and come back to the preview, and then we're going to see exactly what we were seeing before. So if I haven't defined a prefix myself, Neosemantics will generate NS namespace 0, namespace 1, namespace 2, and so on and so forth. But I can use my own terminology, and I can say, okay, let's take these two and go to the namespaces definition, and I can copy them all here and say extract them from there. And we see that it's picked up the two, and it's defined the prefixes that I've named. I mean, I could have called them differently, but like that, I have control on how these namespaces are used. If I go back to the preview and I rerun my preview, now you see that things are prefixed in a much nicer way, right? So that way it's probably easier to identify which things are which. But both are optional. Now you can say, okay, that's fine if I want to be able to regenerate, because of course I need to either keep the whole URI or a reference to some index which will be able to then regenerate it. What if I don't care about it? What if I just want to use public data? I want to query Wikidata just to get a taxonomy of viruses, which is something that I work with Mark Needham for another blog post, or I want to get some geographical data. But I don't care about being able to regenerate it afterwards. I just want to make it nice and usable in Neo4j. Well, of course you can do that too, and you can go to the option where I can say ignore and say I don't care about unique namespaces because I have no intention of regenerating that. So I'll update my configuration, and if I go to preview and I do exactly the same, now we see that things are named pretty much the way we would name it in a Neo4j graph, right? So you see that a plugin, we've completely stripped out the namespace, and we're just keeping the part that's kind of human readable. So that would create the typical Neo4j graph that we're used to deal with. So all this was to show that the preview methods are useful because you can take a fragment of RDF, you can modify, you can change the configuration options, and there's many more that I'm not going to go into today because we have limited time. You can try different things until you say, okay, that's how I want my graph to look like. And when you're happy with it, then all you have to do is go to the import section and just click import. So as you can see here, I mean, we're using the same URI. When I click import, what I get is a summary of the execution. Okay, it's terminated successfully. 19 triples have been imported, and there's no additional information. Like I mentioned before, you can do it similarly by copying this fragment of Cypher and pasting it here in the browser, excuse me. But as you can see, we now have data stored in our graph, and if I look at what's in it, some nice coloring, but you see that it's pretty much what we were seeing, except that now it's already being persisted in Neo4j, right? Good. So that's kind of the import part, right? So we can get any data set imported in Neo4j depending on how we want to use it afterwards. Any questions on this?
No, that makes sense.
Cool. Okay. So let's look at the other way around. Let's look quickly at, and I'm going to create another database for these. Let's say I'm going to create a movies database. Movies, right? And I'm going to use movie. Right. So I have an empty database. What I'm going to do is, was that a question?
Sorry, I was making a joke. I was going to say if they're movies, are they about cows?
Didn't hear that one.
He was joking. He said if they're movies.
Movies. Oh, you
about
know that there is a recommendation engine that's called something like movies with and yeah, and the logo is a cow, of course. But right. So yeah, this is the movies database. So I'm going to just play it just to show how would it happen in the other way around. So I have a graph, a simple property graph. It doesn't come from RDF. It's not the result of importing any RDF data. It's just the typical Neo4j graph that you would have. And I can see, for example, people acting in movies, etc., etc. So that's a graph that I'm sure you've played with. Let's say we want to expose it as RDF. We want to make it public. We want to publish it as RDF for RDF consuming applications. So I can try it from here, but I can also use the app, which is going to make my life a lot easier. So I can go to, interesting, it hasn't picked up. What if I reload? There we go, connect to the active graph. And I'm going to go to the movies database now. I'm going to create the constraint as usual. It's not going to be useful here because I'm not importing any RDF, but it doesn't hurt to have a constraint. So I'm going to go straight to the export side. So like you can see, export is implemented as an unmanaged extension. So we can query these endpoints through HTTP requests. And you see that it's mounted on I didn't show that, but I can quickly show that to you how that's done. The only configuration element that's required, if we go to manage and you go to settings, you probably have done that before, but when you deploy an unmanaged extension, all you have to do is where to mount it. So I've installed it. I mean, I've set it, RDF as the endpoint, but you can use whatever term. So what that means is that I can send my requests to RDF. Then I have to put the name of the database that I'm using. In this case, it's movies, so it's that one. And then all I have to pass is the unique identifier. We don't have URIs as unique identifiers, but we still have a way of uniquely identifying things in Neo4j, which is their internal ID. So for example, if we take Keanu Reeves here, we see that its ID, well, interestingly, is #1. Good. So that's quite convenient because that's exactly the one that I was seeing here. So if I click export here, we see that we see the information about Keanu Reeves serialized as RDF, right? So if I copy this, I can run it as well in let's add this white space here, but you can also run it in the browser. You can see the result of the execution. We mentioned before that there's several formats, several serialization formats. So we can override the default, which is turtle, as you can see, and we can use n triples instead. And this is the one that we looked at before. So this is like a sequence of triples, the same information, but just in a different format. Or we can use the RDF XML format, or I mean, whichever you want. The other one is JSON LD. JSON LD. There we go. And all basically contain the same information. It will require different parsers on the consumer side, but that's the idea. So pretty straightforward, nothing to do. You just need to hit that endpoint and you can immediately see what, the data you have. You can query the data in a number of ways. So it's not only by ID. So you can, if you go to documentation again, where's the exporting section? So you can do it by ID, like you see here, which is the one that we've just seen. Or you can also run a search, for example, by, let me find an example down here. You can run Cypher query. So you can execute a Cypher query and the result of your Cypher query would be serialized as RDF. That's another possibility. Or you can do a combination of label and property. So if you use this syntax, you could get something like, all the matches for a particular combination of let me give it a try for label and label and property values. So for example, if we want to get a, what was it? It was not described, it was, what was it, sorry. So we need to use describe find. So instead of describe, oops, too many jumps. So instead of describe find, and then you would do, for example, movie, and you can get a, I don't know, we can do a search by all the movies released in 99. So if we do movie released and we do 99, no much. Oh, I think by default it does string, but we can pass the value type as integer with the syntax. Yeah, that's the thing with live coding, but you can say parse that as an integer, and then we will get all the movies that were released in, all the matching movies that were released in 99. So that's, so yeah, there's a number of ways of query the graph, and you can extract the data and stream the results as RDF. And Cypher will be obviously the richer option, because it lets you do really whatever you do. Good. So we've covered kind of the import side of things, covered the export, and very briefly, I want to have a look at the model validation part of, you know, the constraint validation that I described. And for that, I have a couple of examples. But again, I'm going to drive from the app, because it's going to make it all a lot easier. So let's create yet another database. So quickly go to system and say, and we're going to do validate, for example, and we're going to use validate. It's an empty one, and well, we can do the same thing we did before. So that's not the one I was looking for. Let me, where did I put the, there is a no, GitHub. Well, I can't type GitHub. It was in one of the repositories, I think is in the datasets RDF. Yeah, I have an example here. There you go. So we have another simple fragment of RDF. This one is about music bands. So we have, I believe, the Beatles and the Rolling Stones. But what's interesting here, because importing these is pretty much what we did before, is that we can define constraints, like I explained before. So, and these are called shapes in RDF. I hope you can read it here. But what we're doing here is defining, yeah, in a way, the shape of the graph that you're building, and the kind of structures that you want your graph to keep. So in this particular case, we're saying that this shape that we call band shape applies, and that's what we mean by target class, to instances of band, so nodes labeled as bands. And what we're saying is that they have to have a name. So a band will have to have a name, and it has to have one and only one name. So the cardinality has to be one. So you can have a band with, let's say you cannot in the real world, but that's what we're expressing here. And the data type for that property is also a string, right? So we can be a bit more granular than the typical constraints that we can express in Neo4j out of the box. We can also say, and that's again a silly example, but we can say that a band will have members. So it will be connected to what the nodes representing the members, the individuals. And we're saying that a band, for some reason, has to have between 2 and 4 members. So we can use this min and max also to control the cardinality of a relationship. So, and like these, we can define some more, right? And how can we leverage these in Neo4j? So let's try it quickly. So first, let's load some data, and the data is here in this file. So I'm going to go to the raw version of this file, and I'm going to import by URI. Let me go with my guide, and I have to, of course, reload, because this one doesn't pick up the new databases. So connect to the active graph and go to the validate database. I create my constraint, and I go straight to import. I know what I'm doing. well, actually I have to configure first. And let's say, for example, that I don't care about the URIs, so I want to ignore them. So that's done, and I go and import my bands. So that's the URL, and it's again in turtle format, so all good. Let's import the data. It's all done. 53 triples in. We can go and check them here. So we have now, oops, a number of let's see, for example, if we look at the member relationship, we see the 2 bands, the Beatles with the 4 members, and the Rolling with the 5. Okay, there you go. There's also information on albums and tracks and more and so on and so forth. We'll skip that for now. So I showed these constraints, the constraints that I was explaining before, which we call music shapes, and we can access them on these URL. So this is a formal definition of these constraints. So I'm going to import them, and I'm going to use the app for that as well. I just need to go to the validation section, and it's pretty similar. So I'm going to pass the URL of the file containing the shapes. I could copy paste them, or I could do all the other options that I mentioned before. But I can say, okay, load these constraints, and the constraints have been loaded, and we see them in a kind of human readable form here. So we're saying that nodes of type band, the name has to be a string, the name has to have a minimum and maximum cardinality of 1, and so on and so forth. Everything we saw there. So the constraints have been loaded now. So what I can do is I can run the validation. And remember that every single thing I'm doing here, you can reproduce it in the browser. And actually, I'm probably going to do that here in the browser now. So I could reload. That's not going to change. But if I reloaded the constraints, let's go. We see exactly the same result. But once I have them, I can say, okay, let's run the validation. And I'm going to do validation. Let's validate. So if I run this method, what I get is a single sort of violation of the constraints. And what this is telling me is that there is a band, which ID is 9. And the only way of identifying it is with the internal ID, because we don't have URIs. And the constraint that it's violating is a max cardinality constraint. And basically, we can see here is that it's an acceptable cardinality of 5. So we can go and see who's this band identified by 9, although we kind of suspect which one it is. You see that ID 9 here is exactly the Rolling Stones. And of course, the issue we're finding is that it has more members than we have defined as acceptable. But I guess that's, I mean, what's interesting, this is a silly example, but you can define richer constraints that can be applied to your graph, and you can get a report of the violations. But what's interesting is that you can also run this in a transactional mode. So there's some other, I mean, you can register a trigger that essentially what we'll do is every time you write to the graph, it will make sure that your transformation, what you're writing to the graph, doesn't go against the constraints defined in our constraints document, its shapes document. Because if that's the case, the transaction will be rejected and roll back. And like this, you can guarantee transactionally that the consistency of your graph is kept. So, right. So, well, that's there's been a lot of talking and probably just coming from me to you, and not much interaction. But I guess at least that has given you an idea of how, you know, how easily, how powerful in a way that the interaction with RDF and semantic technologies is. So import, export, and we've covered validation. We didn't cover the model mapping or the ontologies, but I guess we can do that in another session. Karin, what do you think? Any questions? Any comments?
I was just asking the same thing in the chat room. If anybody has any questions. Okay,
all right.
Michael.
Just a quick question. So right now you're saying, okay, you implemented this constraint to limit the number of band members.
Yep.
So now my question is, so if you tried to add another member to the Beatles,
yeah,
right now, would it reject that, or does it only reject like an entire incoming banned transaction?
No. It will. I mean, the way it works, and as it is right now, it would not reject it because you have to register this trigger. It's all described here in the document. You can see it at if you go to the validation section, validating Neo4j against blah, blah, blah. There you go. So that's the process here. That's validating the whole graph, which is what we did. But you can select the set of nodes that you want to validate, but this is what we're looking at. So what you have to do is you have to register a trigger, and for that there is a method in APOC. So it's as simple as that. So you just give it a name, and you have to pass this, literally hard copying that, just copying these lines. So you copy this to the clipboard and run it. And I mean, you have to enable triggers as well in the configuration because that's kind of an optional element. But once you've registered that, the way it behaves is in a write transaction, you can modify as many elements in the graph as you like. So what this trigger will do is analyze every single element that has been modified by your transaction, whether it's a band, whether it's just a, let's say you modified the property of a member, but you've not removed it. Anything you've touched will be analyzed and checked against the constraints. So it's your whole transaction that will be either passed or failed as a whole. So if your transaction introduces any violation, then it will be rejected. If it doesn't, it will be committed and persisted. But it's the whole set of changes, whether that's a band, an individual, or multiple ones, because you could be writing many of them in the same transaction. Does that make sense?
Yeah, absolutely. That's great behavior. So it's not one or the other. It's going to catch all.
Exactly. And it's, I mean, it will try to be clever in the sense that, I mean, if you're familiar with transactions in Neo4j, so you have sets of basically of elements that you've changed. So you may have added labels to nodes, you might have created nodes, removed nodes. So you can get the types and identify which rules, which constraints you need to check and which ones you don't. Because if you think of these in a, let's say we're talking about a graph with millions of nodes or a set of constraints with hundreds or thousands of constraints, well, it can be pretty heavy. And if you want to run it transactionally, I mean, you want to make sure that you're fine-grained and you only check the constraints that apply to your transaction. But that's, yeah, that's the way it behaves. And yeah, I think that's a pretty cool one. Yeah, good question.
Okay, that's very nice because, I mean, you know, the built-in, baked-in constraints within Neo4j have a number of shortcomings, and that covers quite a bit of it.
That's true, and yeah, they're pretty limited at the moment. I guess this is something that will be extended over time, but there are things that I mean, you may or may not want to, you know. Yeah, I mean, things like, I mean, here you can go as fine and as deep as data types or regular expressions. I mean, let's say I want the name of a person to not include invalid characters, depending on which language you're using or whatever. So you can be very fine-grained and have these validations applied. So that's, yeah, it's a good extension to what you have out of the box with Neo. So that's good. Still not 100% coverage of the whole shackle language, but it's enough to be useful, I would say. Good. So
no, that's really useful.
Excellent. Thanks. So we're over the hour now. I don't know if you, I mean, have to stay a bit longer. Is there some questions?
Yeah, if anybody has any questions, we can ask through it. Oh, Paul joined. I didn't even. Yeah, so Koji asked a question in the chat.
Oh, sorry. Let me bring the chat. Oh, I was not reading. Sorry, because I was in.
Oh, that's okay. There wasn't any. I will let you know if there's any questions that are. And hello, Paul.
Yeah, hello. I'm just realized that there is some time zone mix-up from my end.
Oh, sorry.
Yeah, no problem. I thought it was just about to start, but it's about to finish. I just guessed.
Well, if Jesus doesn't have a hard stop, you could probably.
No, we can stay. We can stay up. And I'm actually. I have another presentation in like an hour, but I can stay a few more minutes. But in any case, it's been recorded, so we'll.
Yeah, I will check the recording instead.
But yeah, no, I can stay a bit. And on the question from Koji, can I compare to RDFs on, I mean, the way you would do it, I mean, that's a good question. Is I guess no, you can't. I mean, there is not a function that helps you point at two data sets, two RDF data sets, but I guess you could, I mean, the question here is whether you want to compare them before or after you've persisted them in Neo4j, but you could of course import them separately and then do the comparison, or import them in separate graphs and then do a structural comparison in the graph. But no, it's a good one. It's not, it doesn't, but that would be relatively easy to implement, because the library that we use has this capability, and it's something that I use extensively in the unit testing, like doing the delta between two data sets. So do you have any example or type of use case where you would find these useful? Because I'm making a note of this, because well, I mentioned before that this is part of the Neosemantics Labs project, and here it's all about hearing how the community is using these projects. So things like these are extremely useful. So oh yeah, so you mentioned code versioning. Yeah, that's the thing is, typically, you know, with RDF, you would I mean, they would be typically additive data sets, because I mean, if you're coming up with a new version, you would probably give this new version different URIs. So you've seen that resources are uniquely identified with URIs, and if it's a new version of a document, or if what you want is an incremental load, I mean, what you can do definitely is, let's say you have version 1 and then version 2. If you load version 1 and then you load version 2, which is the same plus some additional triples, that will not duplicate the existing ones. It will always, you know, just take the added ones, precisely because of the unique identifiers in RDF. Now, if what you want to do is identify the delta between the two files, that's probably a function that would fall in, I would say, in the preview category. But yeah, I mean, that's an interesting one. I'll make a note of it. But at the moment, there is no delta capability in the. You would need to, like I say, either persist it and then find the difference. So yeah, RDF. Good one. You're welcome. What any other questions?
Paul, if you have any specific questions, you can feel free to ask.
No, I haven't. No, I was just.
Is...
I was interested in the subject, so I will watch the recorded session and go from there.
Okay, and you could always use Jesus. Go ahead, Jesus. Sorry.
Yeah, no, I was curious to know what. Hang on, I can't see your name. Paul, right? You said that you were specifically interested in RDF, or is that something that you work with, or is just you're more on the Neo4j side?
I am absolutely 100% on the Neo4j side, right. But there are a few projects which are in RDF world, and
right.
I'm sort of communicating sometimes with people involved with that. So I was just more of a personal interest on see how their lingo works and what I can do with it in the scope of Neo4j.
Yeah. No, that's well. It's a shame that we've missed you, but yeah, I mean, what I've done, essentially what we covered is I did a quick introduction to what RDF and how what RDF is and how it relates to the model that Neo4j implements, the property graph. Yeah. And then I spend most of the second part, I would say 75% of the session, running hands-on examples of the type of interactions, the type of integrations that you can. Yeah. That you can.
So I will be watching your session, recorded session. Yeah. Sure. Yep.
Excellent. But I did cover importing RDF from any public data source into Neo4j and persisting it. We covered exporting. So when you have a property graph and you want to present it, you want to publish it, serialize it as RDF, you can also do it. And we did just a little bit at the end of validation. You might be familiar with Shackle, which is one of the standard W3C standards for defining constraints on a graph. So it's a way of defining, the shape, the structure that your graph needs to have, and you can use it to detect inconsistencies in it. So that's another feature of this RDF plugin that I was presenting today.
Yeah.
So
Yeah, it sounds interesting. I'll be screening it. Yep.
Excellent.
Cool. Thank you, Jesus. Thank you.
No problem.
And thank you guys for coming and helping the community. Paul, did I have a question for you? Did you get the calendar invite, or did you find out about it a different way? Is that why you, because
I did get an email, and I sort of did a calculation on when the New York time zone, the Eastern time New York was related to the time zone I'm in. And just now I found, and if you click on the link, then you will get the right translation, because I mixed up. I did a miscalculation in my head.
Okay. I was trying to put it in the calendar so that way there wouldn't be a discrepancy. So I'm like, I don't know what else I could do that would be good. It's going to be better for that kind of stuff.
Yeah, perhaps I should rely more on the links which are presented in the mail instead of doing it from the top of my head.
Yeah, I mean, I do it that way too sometimes. So it's, but I was hoping that it was going to be a little bit clearer, but.
Yeah, well, yeah. That doesn't matter. I mean, you can't put it in all the time zones everybody is in. So it's just something I will be aware of next time.
Okay. Is there anything that you guys want to see like coming up in the near future? I'm just gonna stop.